let's look at horizontal circular motion in particular. And we're going to look at two examples of this, banking and the conical pendulum. So if we look at my little diagram here, you're going to have to, in your head, be thinking that this is a three-dimensional thing. So the car is going straight into my whiteboard. So this is the corner, this is the profile of the corner, and we're looking at the tail lights of the car. So you'll see that we have an angle that the curve is banked at, and we can draw a free body diagram, a force diagram, showing the forces acting on our car. And we've already done this in centre of mass, so this is purely revision for us. We already know how to do it. We've got our weight force acting straight down, mass times the acceleration due to gravity, and we've got our response force coming up out of the ground, holding up the weight of the car. Now, these are not balanced. These are not equal and opposite forces. So if we look at it, there will be an inward acting force. Now, we're mostly familiar with the idea of an inward acting force on a slope like that. We're mostly interested in, is the thing going to slide down the slope? But we know that cars don't slide down banked corners in general. And we know that cyclists, for example, in velodromes use the curve of the velodrome to their advantage. So what happens is when the car's moving, when the car has a velocity, in this case going into the board around the corner, we know that that inward acting force can act as a centripetal force that acts to turn the car around the corner. And it depends on the size of the angle, theta. And we can find it. We can resolve these vectors to find that inward acting force. And in fact, most of our worked examples will do that. A very common sort of question in horizontal circular motion is how fast or what's the maximum speed that the car can have going around the corner. And of course, what you're looking for there is if there's an inward acting force, how fast, what's the biggest value that V can have for that F? And so you'd use the F, you know, the M and the R to find that V. What's the biggest speed the car can be going at? And sometimes the question will go further and ask you to compare it with a flat corner of the same dimensions. And we're going to do some examples of this with cars, with bikes, and with planes. Now, if we move over here and we look at the conical pendulum, and you're already familiar with ordinary pendulums, just like with the car, you might be tempted to look at it and go, well, I know what's going to happen. This is going to swing in and out. It's going to be a pendulum. And yeah, absolutely. But you've got to remember that this is a conical pendulum. It already has movement in its third dimension. It's moving into the board. So if this was a real thing, it would be turning in a circle like that. And that's why it's called conical pendulum, because it makes a cone surface. So we set up exactly the same scenario again. We've got a weight force pushing it down. We've got a tension force in the string this time. And we've got an angle that our string makes to the vertical. And again, the tension force and the weight force are not balanced. And the inward acting force depends on the size of that angle. And we can find it using trigonometry. We can find how fast this can go. We can find the maximum speed that it can have. And it may seem like this is a fairly trivial thing, but if you think about, for example, all those rides that you find at fairs and adventures, things, I don't know, amusement parks, I think is the correct term, the ones that, as you turn, they pull out. Okay, so you can think about specific examples where this would be useful to know. So, yeah, we're going to solve some problems about this in class, but for now, you just need to be thinking about, do I know how to resolve forces? And if the answer is yes, then you're well on your way to being able to solve all these horizontal circular motion problems with absolutely no issues whatsoever.